Welcome to part 4, and number 14 requires a lot of reading and sorting out. They've got some interesting choices, A, B, C, D, E, so we don't want to go leaping for them. We really need to read. So I have laid out Eastern and Western just to keep those numbers straight. This is the P and the Q for each one, P and Q. But what are they really asking us for? So after we get through all the details, they're asking, what is the mean? But don't stop there. If you stop there, you might be tempted to do this bottom line here and calculate a mean. And it really doesn't make any sense to compare these two numbers. This one is about 13, and what is 12 times 4? That one's about 48, right? With these two different sample sizes, it wouldn't make any sense to compare the mean of Eastern and the mean of Western. It is the mean of the sampling distribution. Wait for it. What are we sampling every time? We're sampling a proportion. Okay, so we're looking at the sample proportion, the average result of getting all these sample proportions. Well, the average result of sampling is going to target the population proportion, right? That's P Eastern, and this is P Western, and that's what the sampling average is going to target. Now, what are we doing? We're doing the difference. So that's picking apart, or maybe not picking apart the question, reading the question very carefully before you jump to the answer. So really, they're asking for this number minus this number, and that's why this is the correct answer. Before we leave number 14, I do want to point out that B was an interesting choice because this is what is the standard deviation. So if we change the question, what is the standard deviation of the difference, then B would be the right answer. And what's the difference between A and B? You would just have to keep the numbers straight. 120 does not go with the Eastern numbers, so that one was wrong. So this is the correct answer to a different question. For number 15, we need to know the central limit theorem and what it tells us about the sampling distribution being normal. It's either the population that the sampling is coming from is normal, or we have a big enough sample size, and the sample size being big enough is defined as being greater than 30. So let's take a look at which of these follows one of those conditions. Well, here we have check, so that one's okay. We're looking for the one that does not make it appropriate to assume the sampling distribution of the sample mean is approximately normal. By the way, that word approximately important to keep in there. It turns out, well, let's see, B, random sample of 50. Here we've got both. We've got a large enough sample size and we've got a bell-shaped population. So we're good. Let's take a look at D and see why that's okay. The population is skewed, so we're a little bit worried there, but we've got big enough sample size. Also, E, troubling population shape, but we're okay with our large sample size. So the only one that doesn't fit is N is too small and the population not normal. In 16, I've read through the problem and pulled out some of the key numbers here, and it looks like they're setting us up to solve a probability problem, but really they're just looking for the formula for the z-score. So what is the formula for the z-score? We're interested in this distance over here. How many standard deviations away is that? Well, at first we look at the value we're interested in minus the mean. So there are a couple distractors where they reverse these, but the 27 comes first. And then we divide by standard deviation. Standard deviation in a proportion scenario uses this formula of PQ over N. So we would just want to put in our, not the 27, right, but the percentage that we're trusting from the government, should we trust the government, and then its complement, 22 and 78 add up to 100%, and then the sample size. And you look for that choice, and that choice was letter B. Number 17 has another sampling situation, and we just want to be careful not to confuse that says mean here, so that's tempting to use this mu formula, but it's mean, keep reading, of the sampling distribution of the sample proportion. So we're actually talking about a percentage here, not a number. You know, if you multiply these together, you'll get something like 1.375, but that's not what we're doing here. We're not talking about the mean number. We're talking, the mean number of chips, 1.375. We're actually talking about a percentage. We're talking about this over here. And what is the average sample proportion? It is just P, which is just 27.5%. So that narrows down some of the answers. But what do we do over here for standard deviation? Again, it's not the standard deviation of the number, somewhere between 0 and 5. It's the standard deviation of the proportion. So we are going to use this formula instead, which is P and Q and N. So that gives us letter C. Here's a good thinking problem. If you know this formula for the sampling distribution standard deviation, you're being asked to say which situation would give you the greatest number. Well, what makes this number go up, right? Let's start with the denominator. The denominator, if you have a smaller number here, so as this goes down, that will make this go up, right? So a low sample size, or a small sample size. Wait, let me get rid of these blue marks, and then I'll write small. So a small sample size will be one of our creators of large sigmas. And then what's the other one? Well, you might have to think about this a little bit. If you've ever done a maximizing of rectangular area problem, you'll know that rectangles like this do not use up as much area as rectangles that are more like squares. So what does that mean for us? I mean, try it out. Multiply a P times a Q like that, and what do you get? This is something like exactly like 0.0099, right? But what if it's 50-50? If this is 50-50, then this is 0.25. So this numerator is much larger the closer P is to 50%. So we want closer to 50-50. Well, I mean, in this problem, we're looking for the greatest standard deviation. So which one does that give us? Well, we want the small n, and we want the P close to 50%. Answer E. A little footnote to number 18. This fact that the variability is higher when we're close to a 50-50 situation is what makes calling elections so difficult these days. I mean, think about it. If we were trying to predict something where, someone had 10% of the vote and, 90% of the people were in our sample were not going to vote for them, it's easier to calculate that margin of error because the sigma is so low. But when we get to 50-50 situations, as in most of our presidential elections, we have a high sigma, which gives us a harder interval to zoom in on the truth. Quick answer to 19 is yes. The sampling mean is going to equal the population mean because of the central limit theorem, and one of the requirements has been met, and that is the sample size is over 30. Another quick answer is that the sample mean is used as an estimator for the population mean.